I'm Dominik. I'm from Miden, and I want to talk today about why I don't think we only need to add ZK to blockchains, but especially in the context of Ethereum, we also need to think about state to make full use of ZK. And I want to talk about how thousands or maybe even millions of actors can prove their state transitions in parallel. So two key properties that we really need from any layer 2 or blockchain, basically, first, it's scalability. This is why we built this stuff. And the second one is privacy. And for scalability, what we want is that thousands of users transact at the same time. If we really want to compete with Cash or NASDAQ. And for privacy, we simply want that Alice doesn't see what Bob did. And just to emphasize the privacy part, because I think it's not really clear to everyone, I really think like AI is taking our jobs. In the sense of, if we still keep building transparent chains, and think about if you would have a chainalysis tool on your mobile phone, like an AI agent, where it just input your Ethereum address, and it would, in seconds, link that to every transaction that you've ever done, to every layer 2 you've ever used, and maybe even to your real-world identity. And we know that this is possible. We know that the chainalysis exists. It's just very expensive. But I could even do that today. But imagine we can do that with our mobile phone and ChatGPT in 2 years. And so I think we really need a blockchain that has privacy built in. And the problem why we cannot have this on Ethereum is basically global shared state. So we have a global state tree, and the tree is being updated sequentially, right? So one transaction after another is being updated to this global state tree. And there are ways to parallelize it, but they were not really fruitful so far. That is because we always touch the same smart contracts. But another problem is that state transitions, they need to be transparent to be verifiable. So every block producer or every client needs to at least have the data to re-execute this transaction. And this hinders us to get privacy. Like, we can later add privacy on top and try to hide information again, but this will always be way more expensive than a native Ethereum transaction. And so we say, what if we would transact at the edge? Like with edge computing, we could also build a blockchain that executes transactions at the edge, and we can have zero-knowledge proofs that ensure the correctness of my behavior. And in that way, like, we don't only need efficient zero-knowledge proofs, but we also need to change the state model. And for the scalability part, we suggest the actor model, where the transactions are executed at the edge or by the actors, and they can do that in parallel, which will give me a lot more scalability. And for privacy, we can have efficient client-side proofs, and the network only verifies the state transitions of the local actors. And just to reiterate quite quickly, most of you have already heard it, I guess, how the actor model works, but it is a model for high-performance databases, and we can think of actors as little state machines with inboxes. They communicate via message passing to trigger state changes in one each other, and these messages can be produced and consumed asynchronously. So it kind of looks like this. We have different actors, they send messages to each other, but stuff happens at the same time. And on Miden, we have built a blockchain around that model, but you can think of, you could also think of this state model being integrated into other blockchains. But like, basically, how we implement the actor model is, like, our actors are accounts. And you can think of like Ethereum accounts. So they maintain state and they expose interfaces like a smart contract, and they send messages to each other. We call them nodes, and these nodes carry asset, and they have spend scripts. And in our model, 2 transactions are needed to transfer an asset from account 1 to account 2. So in the first transaction, account 1 would change its state, transfer 3 tokens to the node. And in the second transaction, account 2 would consume this node and incorporate these assets. And this is different to Ethereum, right? Where Alice sends something to Bob in one transaction, but you need to change the state of Alice and Bob at the same time. And so our accounts on Miden look pretty similar to Ethereum accounts. So they are smart contracts with code and storage, but all assets are natively stored in the account itself. So there is no ERC20 contract that would hinder us in asynchronicity or scalability. Because like if we only would have one USDC contract, then 1,000 of people want to exchange USDC, then we will always have this global lock on every state transition. But here we can, you can basically send USDC at the same time as your neighbor because the asset is stored in your account itself. And nodes, they look like this. They have a script, like a spending script. They define rules for consuming this node. Anyone can execute the node who has the data of the node and consume it. And nodes can carry multiple assets and inputs. And basically, you have a Turing-complete virtual machine that can encode as a spending condition almost anything you want. And so, like what we suggest and what we implement for Miden is that we redefine what a transaction is. And a transaction on Miden is the state transition of a single account. And this makes sense if we want to follow this actor model, right? So actors are little state machines, independent from each other, responsible for maintaining their own state. A transaction is defined as the state transition of exactly this actor. And so as an input of the transaction, you have an account, only one single account, and this transaction outputs the account in a different state, and it can it can consume several thousand nodes and produce nodes in changing its state. So, and then the clue is, or the catch is that every transaction defined as the state transition of a single account is always be proven. So there's a proof for every single transaction. And this is also different to more like most ZK EVMs works, for example, where you would prove the block. In Miden, you prove every single state transition, and then you can batch these proofs together. And the thing is, now, because we combine the actor model with zero-knowledge proofs, basically, we have provable state transitions that happen in parallel by all these actors, and this gives you way better scalability properties. And the cool thing is, you get privacy for free. Because if you prove your own state transition locally, then all the network needs to know is just the public input to your transaction, and this can just be defined as like a set of commitments. So in Miden, you get privacy because the users execute most and prove most transactions locally, and you get scalability because the network doesn't need to execute them or store the full state. And in fact, and this is a paradigm shift to what we have on Ethereum, like privacy on Miden is a means for scalability, right? So if you would add privacy to Ethereum or Solana afterwards, it's always more complex and more expensive and more cumbersome. But on Miden, privacy is a means for scalability because people are private and execute and prove on the edge. The network is free to do other things. Okay, but obviously there's a problem with we still need some sort of global state, because if not, then there would be a lot of double spends. So we need to ensure that Alice isn't sending the same node to Bob as to Charlie. And so we have basically 3 different databases as a global state. One is the account database, a nodes database, and a nullifier database. And like the changes to these databases is what we how we define a block. And basically this block is also a collection of verified proofs. And you can think of accounts on Miden, like these smart contracts, they can be public or private, such that we can also allow for a public shared state. So a public account would have its full data completely on-chain, as on Ethereum. So everyone can look at it and see the storage and the state. But you can also have private accounts, and then only a commitment of this account would be stored on the blockchain. And in that sense, you can think of Miden as a layer 2 of layer 2s, or a layer 2 of ZK VMs that basically only prove to the network that this commitment changes. And the same for nodes, basically, or this is the account database. So in the case left, we have a public account where everyone can see the account contents, and everyone can execute against this smart contract, for example. But this account with the orange circle would be a private account, and basically no one knows what's behind it. And the same we can have for nodes, so there can be public nodes with the full data on chain, but also private nodes where the chain only tracks a commitment to this node, and no one knows what's in there or who the receiver would be. And these nodes are stored in an append-only accumulator, like a Merkle mountain range, for several reasons. But like this database stores all the nodes that are ever created. And these nodes can be added to the Merkle mountain range, even if most nodes are discarded. And the cool thing is that the inclusion witness never becomes stale because of this data structure. So even if I don't have the latest state of the blockchain, like it could be 2-3 blocks behind, I can still prove that my node is included there, and I can consume it, for example. And then we have a nullifier database, which just tracks which nodes were consumed already. And this gives me privacy, so to speak. And one core question is then, how can we have public shared state still if we only have a network of actors storing their state locally? And like, because you can store a public shared state, or you can have public smart contracts. You can also replicate, for example, the Uniswap model, like a DEX. And that would work like there are two users and they both want to trade with Uniswap. So independently of each other, they create transactions, or they execute transactions and create nodes. Then these nodes are like intents. So these nodes are targeted to the Uniswap DEX, and they say, I want to swap my asset A against asset B. And then in a third transaction, in a network transaction, basically the Uniswap actor would consume these two nodes, execute the trades, and create nodes back to the targets, like node 3 and node 4. And this would be a network transaction. So the sequencing would also happen in this transaction by the block producer. So this would work similar like on Ethereum. And then like account 1 and account 2 could, or they can reconsume their swapped assets in private transactions or local transactions, and the swap would be completed. And so on Miden, we try to parallelize and have computation on the edge where possible, but we have it sequential and public where needed. And like this, we hope to find like an optimum. Like there are a lot of transactions on Ethereum today which probably don't need to touch public state. And there are some, like a liquidity pool or a DEX, where you definitely need it. And so I think with a different state model like ours, you can give the user the choice, and you can parallelize transactions way better. And like a drawback, for example, would be composability. This is pretty cool when you have global shared state, that one transaction can touch several accounts, and you can build a flash loan. Like, just to visualize it, like a flash loan on Miden would look like this, that like it would work with async messages, because we have these isolated actors, but you would create a node from Aave directed to Uniswap in a first transaction, and then Uni would like do a trade or a swap and create a node 2. The user would consume node 2, do something with the asset and create node 3, send it back to Uni, swap it, and then Aave would re-consume it. And this basically, like, atomic composability is way harder to replicate in this actor model system. Like, there are some ways how we could do it, like with proof batching, for example. So you could say, like, all these 5 transactions you could execute locally and create one proof for them, or like batch 5 proofs together, and then you send it, and then you would run into similar problems as we have on Ethereum today again. But yeah, this is something that we need to work on. For a comparison, basically, on Ethereum, you have this one global state tree shared across block builders, whereas on Miden, most accounts maintain their own isolated state, but public shared state is possible. You would have, as an execution context, in Ethereum, it's global, but transactions can touch any part of the state, whereas on Miden, you can execute against your accounts, and also if other accounts would expose certain functions. But yeah, Miden could, like the Miden model could give you parallelizable execution in a similar manner how Solana is doing it, right? They also have these stateless programs where you inject an account and get an account in a new state out. So I think in that part it would be better. Composability is something that is obviously harder to have when you have these isolated contexts, as I just explained. The verification is easier on Miden if everyone just verifies proofs instead of re-executes transactions. And this is also, yeah, because of this asymmetry, right? Like, it's harder to create a zero-knowledge proof, but it's super easy to verify them when you just check this polynomial. But executed transaction on Ethereum can be quite cumbersome, depending on which parts of the tree you would touch. And the cool thing, I think, what is really needed is that we get privacy by default. And like, I really think that even if it's a neglected feature on blockchains today, I really think we need that, and not to launder money, but just because I really want that a lot of people will be using blockchains in the future. Like, even my mom should use it. But like, if millions or even billions of people would use transparent blockchains and everyone could always look up what everyone did all the time, it's like would be quite a dystopia, I think. And adding privacy to a transparent blockchain afterwards is just way harder and way more expensive. So yeah, that's it. Yeah, you can think of, I don't know, as Ethereum is this world computer, one large program, obviously, and Miden of these like many small programs or actors that each maintain their own state. That's it.